Hello friends, again I am Shivangoda Virada. I am a PMRF PhD fellow at Department of Electrical Engineering at IIT Delhi. So I am back with my sixth problem solving session. So today's lecture will basically concern about linear transformations. Linear transformations. In linear transformations, we will see whether how to show the linear transformation is 1-1 and how to show whether linear transformation is onto. We'll also see some examples concerning on change of basis, and we'll also look at one of the example which checks whether you have a unique linear transformation or not, whether you have a unique linear transformation or not. So friends, let's start this problem solving session. Yeah. So we'll start with our first question, which says that we have a linear transformation T. So basically this linear transformation T takes a matrix which is 2 cross 3 matrix and gives a and transforms this 2 cross 3 matrix to a 2 cross 2 matrix. So basically this is our transformation. So T takes a 2 cross 3 matrix from this space and give us a 2 cross 2 matrix back. So now the question is, what is the dimension of the null space of the T? So T is a linear transformation. T takes a 2 cross 3 matrix and gives us a 2 cross 2 matrix. The question is, what is the dimension of null space of this transformation T? So, so the null space means, okay. So the null space or the kernel of T is set of all A belong to this space, such that the transformation T on when operated on this matrix A gives us this matrix. Okay, the zero matrix. Let us call this is a zero matrix. So the kernel of T is set of all such matrix A, which when operated by T, gives us a zero matrix. So so the question is, what is the dimension of this space, the kernel of T, or the null space of the transformation T? So let us assume that our A is this matrix, which belongs to R 2 cross 3, the space R 2 cross 3. So when we operate the transformation, the linear transformation T on this matrix A, we get this. So this means that A belongs to kernel of transformation T. So we know that the transformation of this matrix A is equal to this matrix, which is already given in our question. Right. So this is already given to us. So we'll use this, and because the A is in kernel of the transformation T, we get this matrix, a zero matrix. So from this, we can calculate what are the values of A11, A13, and A12. Let us see what we are doing here. So A11 equal to 2A12 and A13 equal to 2A12. So these are the two equations which we get from these two equations, right? So what we see here is that let A12 is equal to alpha, then A11 would be 2 alpha, A13 would be 2 alpha, which means that A11 is equal to A13 is equal to 2 alpha, right? So now this matrix would look like this. Okay. So the null space of the transformation T would be set of all these matrices, right? So basically this would come from this. So remember, if alpha can be anything in a real number. Okay. but we'll take alpha as 1. Then this would be 2, 1, 2. Okay. These are all zeros. This can be all zeros, or this can be 1, this can be 1, this will be 0. We are basically calculating the basis of this matrix. Okay. So looking at the basis of this matrix. So basically, we will look into basis of this matrix. We'll look into the basis of this matrix. Okay. So if you calculate the basis of this matrix, you will get these 4 matrices. This matrix, this matrix, this matrix, and this matrix. So the null space of the transformation T has 4 matrices. So the dimension of the null space of this would be 4. Therefore, the dimension of the null space of the transformation T is 4. I hope you understood this. So now, let us say that we have 2 linear transformations. One of the linear transformation is T, which sends R4 to R3. We have another transformation S, which sends R3 to R4. So one more important information which is given to us here is that T composition S. So we have T composition S, which can also be written as TS, is an identity map, which means that T composition S, when operated on any vector x belongings to S, x belonging to R3 would give us X. Right. So this means that T composition S is an identity map on X. So identity map on X, which means that when you operate a transformation I, so I is 1 0 0 0 1 0 0 0 1. So this would be your identity matrix. When you operate this identity matrix I on any vector X belongings to R3, then you will get the same vector X. Okay. So this is what your identity map is. So now it is given to us that this composition of 2 linear transformation T and S would give us an identity map I. So the question now is, which of the following is true? Is S composition 2 an identity map? This is the first question. So we have to check whether which of these following 4 are true. The second argument says that S composition T is 1 1 but not on 2. The third argument says that S composition T is on 2 but not 1 1. The fourth argument obviously says that neither S composition T is neither 1 1 nor on 2. So let us check how this works actually. So this is given to us. This is given to us. T composition S is an identity map. The first argument says that S composition T is identity map on R4. So why is okay? So we have to check whether this is true or not. So this is given to us, right? This is given to us. T composition S is an identity map X. So this is not right. So let us say that there is a matrix A belonging to S. Okay. So which means okay, A belongs to S, which means that A is a matrix of 3 cross 4. Okay. And B is a matrix of 4 cross 3. So we have this type of thing. So we have T composition S, which is an identity transformation. So let us say that A is from S and B is from T. Okay. So T composition S would give us this. So first A which belongs from S is operated on X, and then B which belongs to T is operated on A of X, which would give us the same vector X. So basically BA into X would be X and BA is equal to I. So now the question is S composition T an identity map? So this means that this means that so we had this right. Now if we inverse the position here, if we take A here and B here, we would get this. So A into B, where Y belongs to R4 here. Okay. If A into B of Y equal to Y, Is this true? Remember that AB from this is not equal to BA. Right. Remember BA, which is equal to I, is not equal to AB. So this means that S composition T is not an identity map. So now let us run on to the jump onto other argument which says that S composition T is 1 1 but not onto. Okay. So it is given to us that T TS or T composition S is an identity map. So this implies that T composition S is bijective. T composition S is bijective implies that S is 1 1 and T is on 2. So given this and saying that this composition of two linear transformation T and S is an identity map tells us that it's bijective, and this argument tells us that S is 1 1 and T is on 2. Okay. So now let us see that we know that T is a transformation which takes a vector in R4 to R3. So just by seeing the dimension of this, we can say that T is not an 1 1 transformation. So how is this done? So T is, so let us say that A is a matrix belonging to transformation T, which is of size 4 cross 3, right? This is 3 cross 4. Okay. Now the rank of T is minimum is less than or equal to minimum of 4 comma 3. So this would be 3. Let us assume that rank of T is equal to 3 at this point of time. Okay. So by this, I can say that the nullity of this transformation T is equal to 1. So which means that the null space is spanned by one vector, one basis vector. So transformation of T when operated on zero vector would obviously give us a zero vector, which is a trivial solution. But since the null space is spanned by a vector, spanned by a basis vector, let X belong to null space of the transformation T, which implies that Tx equal to 0. Okay. This says that T is not a 1 1 transformation, because no, if we have a zero vector here in 1 1 transformation, there is only a T here can give us a T 0 here. But now there are x1, x2 and a zero vector. So all are going to a zero vector here. So this is not a 1 1 transformation. So in 1 1 transformation, the dimension of null space is not equal to 0. Okay. So now let us see the transformation S. So S is a linear transformation which takes a vector R3 and sends us to fourth dimension space. So let us say that A is a linear transform belong to S. Okay. So A is a 4 cross 3 matrix. A is a 4 cross 3 matrix. Again, the rank of A is 3. So let us assume that A looks something like this. Okay. So since A is a rank 3 matrix, if we perform a row reduced echelon form, we would get this type of row echelon form corresponding to A matrix. So we have one of the row as a zero row, and these are XYZ which belongs to R3. So if we multiply this, then we would get B1, B2, B1 tilde, B2 tilde, B3 tilde, and B4 tilde, right? So which means that this is true. Okay. So here B4, so the range space of A has a non-zero B4. Okay. So if it has a non-zero B4, then this type of vectors will not span range space of S. This implies that S is not onto transformation. Okay, so this says that S composition T is neither 1 1 nor onto. So now let us jump on to the fourth question. So in fourth question, we have a matrix A, and we are told to see which of the followings are false. So the first argument says that there exists a non-zero vector of R3 which is not in range space of A. There exists a non-zero vector of R3 which is in kernel of A. There exists a non-zero vector of R3 which is not in kernel of A. So let us see this. This is actually an easy question which will basically depend upon the rank of A. Okay, rank and nullity of. So let us see how this problem can be solved. So the first thing which should be done is to calculate the rank of this matrix A. So that's what we have done here. So rank of matrix A is equal to 2. So which means that there are two vectors, two basis vectors, which spans the column space of A. And these vectors are 1 1 0 and -1 -2 1. So these vectors comes from here. So these two vectors spans the range space of A. These two vectors spans the range space of A. Okay, so this is a plane in R3. So the nullity of A would be 1. Okay. So using this information, we can see that there exists a subspace perpendicular to the range space of A, which we call as range space of A perp. Okay, we call this as range space of A perp, which is perpendicular to the range space of A. So our range space of A is a plane. So this is, let us say that this is a range space of A, and there is a vector, and what is the subspace? So this is a plane which is your subspace, and there is a line. Okay, there is a line which is perpendicular to this vector. Okay, so this is your range space of A perp, and this is your range space of A in 3 dimension. Okay, so this is your subspace, and this is a subspace. A line perpendicular to this plane is a subspace which is perpendicular to the range space of A. So this range space of A perpendicular or perp is not spanned by range space of A. Okay. So this is false. Okay. So this is true. Okay. So this is true because there exists a non-zero vector in range space of A perp which is not in range space of A. Okay. So from rank nullity theorem, not rank nullity theorem, by common sense we say the nullity of A is equal to 1 because rank of A is equal to 1. This implies that the dimension of kernel of A is equal to 1, which means that the null space of A is spanned by this vector. This only one vector, one basis vector, and that is this vector. So this implies that there exists a non-zero vector of R3 which belongs to kernel of A. Okay. So this implies this is also true, not false. So the third argument says that there exists a non-zero vector of R3 which is not in kernel of A. So again, we'll use the same perpendicular basis argument. Okay. So the answer is yes, this is true. Okay. This is true that there exists a non-zero vector of R3 which is not in kernel of A. So remember the kernel of A is a vector 1, 1, 1, right? So there exists a non-zero vector which is not in kernel of A. So if you take a perpendicular of this line, so let us say that 1, 1, 1 is this vector. Okay. So if you have another line or a plane which is perpendicular to this line, let us say that this plane is perpendicular to 1, 1, 1. Right. So there is a vector which there is a non-zero vector which does not lie in the kernel of A. This is your kernel of A. So and this subspace which is perpendicular to this kernel of A is not in kernel of A, right? Okay. So this subspace, in this subspace there exists a non-zero vector which is not in kernel of A. So this is also false. So the answer would be this. These are false. These are true. This is true. This is true. So answer is this. So let us move on to the fourth question. In fourth question, we have a linear transformation T from R3 dimensional space to R3, and we are given the basis B, a standard basis, which we call E1, E2, and E3. Okay. So we have a standard basis E1, E2, and E3, and we have a coordinate. We have a coordinate matrix P B to B, which is this. So these are our coordinates. Okay. So we have to find the image of this vector. Okay. So we have a linear transformation T which we applied on 100, which is E1, using the coordinates. These are our coordinates, and this red part is used here. Okay. So TE1 is equal to this this linear combination. Then again TE2 would be this linear combination using these blue coordinates here, these blue coordinates. And then T of E3 is a linear combination using these three black coordinates, which corresponds to this thing. So the image of this 212, this 212 can be expressed as a linear combination of these three vectors. This is E1, E2, E3. These are our standard bases, and these belong to basis B. So E1, E2, E3 belongs to this basis B. We take a linear transformation of this vector as T into this, which would give us this thing. Since T is a linear transformation, we can take T inside and operate on these vectors. Okay, we would get these vectors. We would get T of this vector, T of this vector, T of this vector, and T of this vector. So this would give us this as given in previous thing. So the addition of this would give us 333. So T of 212 is this. So this is your image. Image of 212 corresponding to the linear transformation T. So now let us move on to the fifth question. So here we have a transformation T from R3 to R3, and you have been given two bases, B1 and B2. And B1 is given as E1, E2, and E3, whereas B2 is another basis set which is given by U1, U2, and U3. U1 is this, U2 is this, and U3 is this. E1 is this, and E2 is this, E3 is this. Okay. And we have been given the coordinate matrix T corresponding to linear transformation T from basis B1 to B2, and that coordinate matrix is this matrix. So we have to find a coordinate matrix from B2 to B1 corresponding to this linear transformation T. So this is actually very easy. We have to first express TE1 as a linear combination of U1, U2, U3. Okay, TE1 as a linear combination of U1, U2, U3. Then TE2 as a linear combination of U1, U2, U3. TE3 as a linear combination of U1, U2, and U3. So this is what we have done here. So this comes from your coordinate matrix. Okay, from here. This comes from your coordinate matrix. This comes from your coordinate matrix. This comes from your coordinate matrix. Okay. So now let us consider an arbitrary vector xyz. So we can write this xyz as a linear combination of your standard basis vectors. Then we will transform this and we'll get this vector. So now we'll have the linear transformation of u1 and feed these three numbers. This is x, y, z, and feed these numbers to get. We feed 1 to get 1 to 1, 1 to 3, and 2 to 2. So a coordinate matrix transformation from B2 to B1 using this linear transformation is this. Now let us consider transformation T from R3 to R3 such that this set of all vectors x1, x2, x3 has to satisfy this equation, which is in the range of T. So corresponding to this, which one of the following is true? So is the first argument says that T is unique. The given linear transformation T, whose range space satisfies this equation, is that transformation T unique? Is T a non-singular transformation? Or whether the dimension of null space of the transformation T is 2, we have to see which of the following is true. So we have been given that T is a linear transformation from R3 to R3. And this transformation T, the range space of this transformation T satisfies this equation. So indirectly, the range space of T is a span of these two vectors. So just by seeing this, I can see that range space of T is not unique. Okay. So if there was another vector here, another vector in the range space, say x, y, z, then the range space of T would have been unique. Otherwise, now it's not unique. So from this, we see that the dimension of range space of T is 2, which means that the dimension of null space of the transformation T is equal to 1. So this basically says us T is a non-singular matrix. Okay. So this is true. I don't know why they have written none of this, but T is non-singular. Now we have a linear transformation T from R3 to R3 defined by this. Okay. So we have to find an inverse of T. I think this is a very easy question. We see that to get this matrix, so this is here and this x1, x2 here. To get this, we need this type of transformation matrix T. Okay. So Tx, where T is this matrix, is equal to this. And T inverse is this. Just a matrix inversion here. And T inverse x would give us this vector. The answer is this. Now let us consider a linear transformation T, where V is a finite dimensional vector space. We have to see which of the following is true. So V, the finite dimensional vector space V, is direct sum of range space of T and null space of T. Or we have to see whether this is true or this is true. So let us take a transformation T, which when operated on this vector xy, give us y0. So this T basically is this thing, right? So corresponding to this T, the range space of T is x-axis and the null space of T is also an x-axis. So this is true. Okay. So which means that the answer is this. None of them are true. So we jump on to ninth question, where we have a vector space V of real polynomials of degree less than or equal to 2. We have defined a linear operator T, which says that a linear operator T which operated on x raised to I for I equal to 0, 1, 2 would give us the summation of x raised to j, where j is from 0 to I. And the basis of the polynomial is 1x x square. So we have to find the matrix T inverse. So let us assume that the second degree polynomial p of x is given like this. So p of x equal to alpha naught plus alpha 1x plus alpha 2x square. So the transformation T of this polynomial p of x would be this. So by definition, T of 1 would be alpha naught, T of 1 would be 1, and T of x would be 1 plus x. T of x square would be 1 plus x square. This is what is written here. So simplification of this would give us this matrix, this polynomial, which is alpha naught plus alpha 1 plus alpha 2 plus alpha 1 plus alpha 2 into x, then alpha 2 into x square. We have the task of finding what this T inverse is. So let us assume that the T inverse of this second degree polynomial is beta naught plus beta 1 x plus beta 2 into x square. Okay. So when T is a linear transformation, right? So T can be sent on this side. This would be T into this second degree polynomial. So again, the T into this would give us this. The similar transformation. Okay. Now we compare on both of this side and see that beta 2 is equal to alpha 2, beta 1 is equal to alpha 1 minus alpha 2, and beta naught is equal to alpha naught minus alpha 1. So this is what we get. Okay. So now T of 1 here is 1 plus 0x plus x square. T of x is minus 1 plus x. T of x square is minus x plus x square, which can be written as this matrix. Okay. So this is your coordinate matrix. So now the last question. So we have a linear transformation T from Rn to Rn, and we have to check which of these following statement implies that T is 1, 1 and onto transformation. So T is basically okay. So T is a linear transformation from Rn to Rn. Okay. So a very simple thing would be to check this by rank nullity theorem, which says that rank of T plus nullity of T is equal to n. So for T to be 1, 1 and onto, the nullity of T must be equal to 0. Okay. So this implies that rank of T must be equal to n. So this also satisfies and this also satisfies. Okay. There are two answers to this. So this is what assignment week 6 assignment problem and solution discussion. I hope you understood some of the concepts, and it's better to keep practicing these questions. Thank you. I think I must stop this now. Thank you.